Our next speaker is Pragati Awasthi, Associate Vice President of Decision Science and Analytics at PNC. Pragati is here to talk about technical debts in machine learning systems. We're excited to hear more about that. Over to you, Pragati.
Hello, everyone. So this session today, I'm going to talk about technical debts in machine learning systems. And this session seeks to spread the awareness and discuss something we might need to consider in practice if we were to continue using ML systems over the long term. With that, I would like to introduce myself. Hello, my name is Pragati Awasthi, and I work as an AVP in Decision Science and Analytics space at PNC Bank. And I have also worked as a data scientist in the past. Data being an essential part in whatever we do, it really inspires me a lot to give it a deep insight. And it's probably one of the reasons I chose this field as my profession. But from that, I have masters in business statistics from Drexel University in Philadelphia. And apart from this, I'm involved in theater, drama, and also involved as speaker with organizations worldwide to support and educate new people in the field of ML and data science. So this is how the agenda for today's session looks like. We're going to first start with talking what's wrong and why we are here, why we are talking about this. And next, I'm going to focus on my favorite topic, which is, I guess, 80% of what we're going to talk today here about the technical debts in machine learning systems, and then move on to some of the key contributors that, may have scored higher in terms of the factors which are the key contributors of technical debts in your ML systems. And then we move on to some of the questions that we might need to ask even before we start thinking of implementing a machine learning system, and then some of the possible solutions or some mitigation strategies that we might adopt and, try to probably not completely fix it, but try to reduce the debt that we had incurred at this point. Okay, so let's get started. Very lately, we have observed that there's a very uncomfortable trend which has emerged where it's very easy to develop anything or deploy anything, or probably might not be easy, but relatively fast and cheaper than, maintaining it or repairing it over time. So that's the first point I would like to present here. It's how we build models, and sometimes they never get deployed, and sometimes even if they got deployed, it really becomes very difficult to, maintain it over time. One of the possible problems also arises when we might have not partnered with right skill sets within the organizations, and we might have missed doing that prior to start the implementation of the ML system. And that's something we might consider very early on the stages when we are trying to implement any machine learning system. And my third point here is more on the development side. I guess it's taken care of when we are building or when we are writing machine learning code or any development code which is related to our machine learning system. So making sure that we are always building a code structure which is repeatable, reusable, and modular in nature. I think that's very important in such cases if we want to change something, and if something changes in the external world, it should be easy for us to come back and change things and good to go. Fourth one is, I think, our favorite, which comes, problem comes when there's a lot of governance and security regulations, probably within the team, within the organization, sometimes some federal regulations as well, which might impose some problems with machine learning systems. So highly encouraged to think about this again very early on, even before starting to get implementing the machine learning systems. And the fifth one, which is actually the main topic of this session, is the hidden technical debt in machine learning systems. And it can, again, come through a variety of sources. It can be due to the different versioning of system integrations and so on. All right, so this is one of the work that was presented by Google in 2015 in one of the conference at NIPS, which clearly, and in which we can clearly see that how ML code is just a very small fraction of a real model systems. That's why just focusing on improving the code or making it reusable doesn't solve the purpose here. I think the purpose is to think about it's very important for us to think about the required surrounding infrastructure as well. And even though if it's vast and complex, but I think it's very important for us to understand and think about the whole system, like a system as a whole, rather than just thinking from like software or coding perspective. So what are technical debts? So generally they are very difficult to detect because a lot of time they are hidden and they compound very silently, and which makes it them even more dangerous. And I think every ML system, they have a special capacity of incurring technical debt, even if we don't see them explicitly, but they all have to be maintained, at certain point if you want to use them for a long time, right? So they do have the problem of maintenance. So probably we have a structure in place in which we try to regularly monitor and maintain the code base, but ML specific issues also gets added to those problems, and that's where this technical debt start getting accumulate very rapidly. And again, I think I mentioned this. So this exists at the system level, which we have seen here. So this is just not a debt which incurred from the ML code, but also a debt which incurred from system level rather than code level. And in general, machine learning systems are inherently complex because they combine a lot of technical issues with software as well as with ML. And there can be a lot of changes in the external world as well, which can influence these issues too. So highly encouraged to think about these, about these debts. Talk within your team, talk to your data scientists, researchers, and DevOps. Very important, and think about these questions even, very very early in stage before even deciding of whether or not you're gonna start implementing that ML system or not. So let's look at some of the risk factors, which are probably not the only risk factors that which can contribute to technical debts, but maybe some of the key factors here, which I can think of now when I'm talking to you. And we might have more risk factors, and I think I'll leave it up to you to decide what other risk factors you can have within your team or organization or any project you're working in. So I would like to start with unstable data dependencies, which is quite common, and I think it's easy to understand, but it's something which we avoid a lot of time. It's easy, but it can be easily skipped. It can easily skip our mind. So something, for example, if input signals are unstable and they are changing over time, and we don't have a provision in place where we are providing that input signal to the model, it can lead to certain imbalance within the infrastructure, and it can create a lot of problems which we might not notice, but it can then lead to outcomes which were not expected when we implemented it. Another possible example is input signal coming from probably another machine learning model, which itself is updating over time, but the way we are ingesting that output as an input signal in our model is not getting changed. So one way to mitigate that is probably to create a versioned copy of the signal. But again, versioning, I think a lot of you will agree with me that versioning itself is a huge cost. So again, this is a mitigation strategy, but probably not the best way of how you can handle this. But again, I'll leave it up to you to decide what you can do to solve this. But this is probably one of something which I can think of, while talking about this risk factor. Second is underutilized data dependencies. wherein there are some, similarly in coding structure where you can have certain packages which you might not use often or which are maybe unneeded at a certain time. So there can be such, packages or such modules in machine learning systems as well, which can make an ML system unnecessarily vulnerable to change. So this is something which talks about that situation. And a common example of it is, when you have a set of features which you included very early on in the development process, but over time you might have got certain more features which makes it the other features redundant, and this can go undetected and may cause various problems, and maybe a problem of correlation as well when you have same features carrying one kind of signal. So this is probably not the only one, and the model can also result in a lot of changes if the external world input signal changes over time. And again, one way to detect this or know about this is to do an exhaustive leave one feature out evaluation, in which you can leave one feature at a time and try to evaluate your model. And if you see your things getting worse or things getting depleted, then you might want to come back and see that what are the features that you might want to take it away from the model or might not want to use it in future. And again, the frequency should be decided within the team, but this should be run quite periodically to remove unnecessary features time to time. Next one is feedback loops. Again, so feedback loop, this can be present in systems which are already live in production. And this is a problem which comes when the behavior of the model changes within itself. So suppose if machine learning systems are getting updated over time, which it may end up influencing their own behavior. One example of this situation is when you implement a recommender system, and then you keep on recommending the same item to the user again and again based on based on their favorite actors and so on. So it might create some output which is actually not what we intend to build when we are building the recommender system. And one way to possibly mitigate this is by doing some sort of randomization or by isolating certain parts of data from the model, and then doing some testing time to time and see if the outputs which are coming out makes complete sense. Configuration depth, it's more on the configuration. So every configuration line within your system or within your code really has a potential of incurring a debt or incurring a mistake in long term. So one of the example of this is when a certain configuration is made and then certain parts of it is gets missed out for a certain time period. For example, if feature X of the signal of the system got incorrectly logged for a certain days, and then after certain days we realized that this is not the way we wanted to ingest this feature on, and then we try to correct that, but the logging which is being done on those days is already there in the ML system, and system is running with those features. So that's where configuration debts start building up. And also sometimes it happens if we are trying to ingest a feature from an external source, and then there is an outage of that source, so we are not getting that signal for a certain period of time. That can again also create some configuration problems as well in the system, and it can also lead to some of the debts, technical debts in the systems. Generally, these are hard to modify correctly or hard to reason about, but mistakes in these configurations can really be very, very costly, and that can really lead to loss of time, loss of computations, and I guess most importantly, loss of the quality of the ML system that you implemented, when you started building that out. what you thought is not what you're gonna get at the end. So this is a famous principle, which was again presented in the paper that I was talking about earlier in the slides that Google presented to one of the conference in 2015, which is changing anything changes everything. So again, these are all seems to be interrelated, but these are all like different, like discrete problems. For example, if there are a set of features, say n features in a model, and if you change the input distribution of one of those features, the importance weights of that particular feature as well as the remaining n minus one features may change. And same thing might also result when you try to add n plus one. So you already have n features and you're trying to add one more feature to it. It can also create same sort of problems, like a not a good balance of the importance weights what it was built on. So, and again, this comes from the principle that no inputs are really independent. So if you're trying to ingest an additional input, it really won't be independent feature. It will have an impact on other features as well. And this unfortunately doesn't just affect the features, but it also affects the way you have done the hyperparameter tuning of when you were building the model, some of the learner settings, sampling methods, converging thresholds, and whatnot. So I think the phrase says it all. If you change anything, it might change everything. So might need to think about that as well. Next one, I think I wrote these down just to take a short quiz within your organization or within your project or team to see where you stand, or maybe like if there is a need for you to talk about this within the team, within the organization, and see if you're also have accumulated a lot of technical debt, or if not, then even before spending a lot of money in building one system, might need to ask these questions even beforehand. So first one is to ask whether or not a new algorithmic approach that you're trying to adopt be tested at full scale, and if yes, then how you're going to test that at full scale. You should probably have that infrastructure ready in mind, or in like shared within the team, that this is how we are going to test our new algorithm or new ML system at scale when needed. And also the transitive closure of all data dependencies that we talked about. So do we have a closure or a transitive closure of all the data dependencies that we might have for the model? And I think third one is most importantly, how precisely can you measure, or can you measure the impact of a new change to the system? Sometimes you can't, but I think having some sort of capabilities to measure this would also make debt probably not zero, but low. And then how does improving one model or signal create an impact on others? This is again a problem or a question that comes from the dependency standpoint too. And last one is just doing a dry run, that how you can quickly make your new member in the team brought up to speed for machine learning system, how fast they can get adapted to it, and how can they start feeling comfortable using it, right? So if they can, probably that's where you can think that your machine learning system is quite flexible and quite low in debt. But if not, then probably that's one of the signs that you might have to think about this now. Some of the possible solutions, which I feel are not enough here to take care of, but these are like some of the possibilities or some of the ways in which you can get out of debt. But again, this revolves around this is situational, and depends on what you're trying to work on and what kind of debt you have in the system. So talking about some of the coding configurations, so like refactoring code, improving unit tests, deleting dead code is something which researchers and engineers can take care early on in the development process. And then as an infrastructure, like in the infrastructure as a whole, how you can think about reducing dependencies, tightening APIs, have more documentation, which can also, possibly solve for the problem. And if you have more ideas, then I'm open to chat about it. Yes, so as an ML practitioner, I strongly feel that we have the power to address this, and it's super important as well to, for the sake of the health of machine learning systems, and to be able to use that and to be able to have the survival of those systems for a long time. It's super important for us to be committed to pay that debt, no matter what, if you're a Lannister or not. So with this, I'm gonna close this session and also open forum for any questions that you might have for me. And you can also contact me via email and add me on LinkedIn. Thank you so much.
Awesome. Thank you so much, Pragati, for that amazing talk. I definitely learned a lot. I know we have a couple quick questions that came in. We definitely have time, I think, for about two. So the first one here is, how can data scientists and engineers help non-tech stakeholders understand about technical debt and their significance of continuously dealing with it?
I think it's a great question, and I think there's always a communication challenge I've experienced too between engineers doing the technical work and some of the stakeholders. Probably the reason because we always use different vocab and always focus on different things. So there's definitely a gap in there. But when I go to my non-technical manager to say, hey, look, we need to refactor this thing because it is creating some complexity with certain features and its ingestion and so on. So it doesn't really mean anything to them. And what my take on that is, we as developers and as practitioners of machine learning and data science, we really need to try to focus on learning more business-oriented metrics. For example, what time we can, lose if we continue using that, or if we don't fix that, or how much impact it can create on customer. So I think that's gonna matter most to them in order to have, more and more attention and involvement, and as well as engagement to your problems with your stakeholders. So yeah, that's my take on that.
Definitely. No, that's some great insight. That's about all the time we do have in terms of Q&A, though, although I know your contact is listed there, so I'm sure folks can definitely reach out. Also, as a quick reminder, the recordings and the presentations are available, and they'll be available again on demand about 2 hours after each session, so everyone will be able to go back and catch those. But again, thank you so much for taking the time to chat with us today, Pragati.
Sure, thanks for having me.
Of course. And then everyone, we do have a fireside chat coming up. It's with Jesse Bishop from Dataiku and Mike Berger from Mount Sinai. So be sure to follow the pop-up that's going to come up and head on over to that session. Thank you again.